Okay, so this is part 5 in our series on deriving the C5h character table. This is how far we got last time. I just added the rotation matrix for C5 so I don't have to write it out live. And we got to this situation where we had 1, 2, 3, 4, 5, 6 irreducible representations. There were no more functions that could transform. And we knew we were done because 2 plus 2 plus 2 plus 2 plus 1 plus 1 is 10. We have 10 classes. So we knew we were done, but we also knew that there's something wrong with our E vectors because we have 6 irreducible representations and 10 classes. Our number one rule of the character table's mathematical relationships is that the number of irreducible representations has to equal the number of classes. And so the number of classes equals 10. So the number of rows or irreducible representations also has to equal 10. And so what we have to do here is we have to break up all these E vectors, the E1 prime, the E2 prime, the E2 double prime, and the E1 prime, into two components each with containing one-dimensional vectors, irreducible representations. So when we do that, we'll have 8 ones here, 8 rows of ones, across here, plus the original A prime and A double prime ones that we started with. That'll give us 10 ones, and we'll have 10 irreducible representations totaling our 10 classes. So that rule of the character table is satisfied. Furthermore, what we have to do is check that our sum of the squares of the dimensionalities, which is the character under the identity, equals the order of the point group, which is the total number of symmetry operations in the point group, which is 10. So if we have 10 ones here, situation where we broke on all these up in 10 ones, 1 squared plus 1 squared, adding up 10 1 squares is going to equal to 10, which is equal to the order of the point group, which is 10. So that's what we have to do in this video. And so what we're going to first work on is breaking up E1 prime. This is this first one. I mean, we can do any one first, but we'll work on this. So we're going to cross this off of the character table here. We notice that this kind of aggregate E1 prime, how we had it before it was broken up, was transformed as x and y transformed as that. And so we're going to use an imaginary function here that's related to x and y that sort of embodies that character, and that's going to be x plus iy is one example that we can use. And so we're going to ask the question, how do these different symmetry operations, how does one symmetry operation in each class, well, there's only one symmetry operation in each class here, so each symmetry operation transform x plus iy. And of course, x plus iy is going to go to x plus iy with the identity. That's going to get us a value of 1 here, which we already have written down. And the reason why we break it up, right, 1 plus 1 is equal to 2. So this value plus this value is going to equal to 2 cosine 2 pi over 5. Get there eventually. But now we go to the next symmetry class here is C5. So the C5 operation, what does that do? Well, x plus iy is going to go to, the x part of that is going to go to just doing row by column matrix multiplication here for our 2 by 2 rotation vector. Cosine 2 pi over 5x minus sine 2 pi over 5x plus I sine 2 pi over 5x, right? We have a I here plus I cosine 2 pi over 5y. And so this actually ends up being, you can factor out x plus iy here. And when you factor that out, you get cosine 2 pi over 5. Okay, kind of taking into account this term, plus I sine 2 pi over 5y. And just to show you, prove to you that that works, this first term, you get cosine 2 pi, cosine 2 pi over 5 times x, that's this term, so that matches. Your second term here, negative sine 2 pi over 5x. How do you get that? Well, you don't get that because that was written wrong. That should have been a y. Maybe it was supposed to be meant as a y, but I couldn't read my own handwriting, right? So it came from this row by column multiplication here. So this is x term, this is the y term, row by column. So how do you get this? So anyway, cosine 2 pi over 5, let's check this. Cosine 2 pi over 5x, cosine 2 pi over 5 times x gives us this term. How do we get the minus sine 2 pi over 5 y term? Well, that comes from I sine 2 pi over 5 I sine 2 pi over 5 times IY. That's going to get you I squared sine 2 pi over 5 y. And we know that I is root of -1. So I squared equals -1. So that gets a negative sign in front of this. So you get minus sine 2 pi over 5 over y. And then I sine 2 pi over 5 times x, that's this term. And I cosine 2 pi over 5 y, that's this term multiplied by that term. So that works. And if you notice what this is equal to, that is actually equal to something known as the Euler formula. So the Euler's formula, right, is e to the theta I equals cosine theta plus I sine theta. Okay, and so one of these beautiful, crazy expressions of math. And so e to the pi 2 pi over 5 I equals cosine 2 pi over 5 plus I sine 2 pi. That is this, what we have factored out here. So in other words, x plus iy goes to x plus iy times e to the 2 pi over 5 I. And that's going to be such an important quantity in this character table. It's going to come up over and over again. We're going to call it epsilon. So epsilon equals 2 to the 2 pi over 5 I. We're just defining that. And so we can rewrite this as a matrix now where x plus iy multiplied by epsilon is explaining our transformation. Epsilon is our 1-by-1 transformation matrix. We take the trace of that matrix. So the character for C5, or how that explains how x plus iy transforms, is actually just equal to epsilon. So we can put here for our character epsilon. So we're going to do a very similar thing here for C5 too. So next symmetry class we have to worry about. So the C5 2 operation. What's going to happen? Well, x plus iy is going to go the same thing, except now instead of having cosine 2 pi over 5s here and sine 2 pi over 5s, we're going to have cosine 4 pi over 5s and sine 4 pi over 5s. And so all this is going to come out the same thing, and at the end, we're going to get that our chi, our character of C5 2, is not equal to epsilon anymore, but it's equal to actually e to not 2 pi over 5 times I, but 4 pi over 5 times I. And what we're going to do is actually just evaluate that. So that equals cosine 4 pi over 5 plus I sine 4 pi over 5. Well, cosine 4 pi over 5 is just equal to negative cosine 2 pi over 5. So we're going to get negative cosine 2 pi over 5. Okay. Oh, sorry, that's actually not right. Ignore that. So it equals this, okay? And if you actually look at what this is, okay, what you can do is you can take E, kind of looks like, okay, I have a 4 here. What we're going to do is we're going to take epsilon squared. If we square epsilon, what we end up getting is cosine squared, taking epsilon here, right? Squaring it. So we get 2 pi over 5. Plus I squared sine squared 2 pi over 5. Well, I squared is -1. So minus sine squared 2 pi over 5. And then we have these other components, which are these off diagonal terms. They're the same when we square this. I'm taking epsilon squared. So we have 2i cosine 2 pi over 5 times sine 2 pi over 5. Okay. Well, what ends up happening here is that, so we now have to use some trig identities to help us out here. And so earlier we were talking about how, where can I put this? Cosine squared of anything, I use theta, minus sine squared theta equals cosine 2 theta. And actually 2 cosine theta times sine theta equals sine 2 theta. And so this ends up simplifying to, we have a cosine squared something minus a sine squared something. So that's going to be cosine 4 pi over 5. And this part ends up being I sine 4 pi over 5. And so epsilon squared, squaring epsilon, actually gets you what ends up equaling now Euler's formula back, but now with 4 pi over 5i. And that's what we figured out was the character. So another way of writing the character, instead of writing e to the 4 pi over 5i, if we want to do it in terms of epsilon, that just equals epsilon squared. So that's a nice compact way to put the character there. Okay, what about C5 3 times? That's our next one. C5 3 times. Well, now instead of having 4 pi over 5, we're going to have 6 pi over 5. And so epsilon is going to be equal to 6 pi over 5. We're going to get our character, sorry, not epsilon. Epsilon's always equal to 2 pi, e to 2 pi over 5. But we're going to get our character at the very end when we do all the math, which we don't have to redo. Our character is going to be equal to e to the 6 pi I over 5. And that equals, of course, cosine 6 pi over 5 plus I sine 6 pi over 5. Well, cosine 6 pi over 5 is equal to cosine 4 pi over 5. Okay, it's one of these relationships. You just look at the unit circle. And sine pi. So anyway, we got this cosine the character is e to the 6 pi, or 5 times I. Well, cosine, some relationships here. I guess I can write out. Cosine 4 pi over 5. Whoa. Wrong button there. Cosine 4 pi over 5 equals cosine 6 pi over 5. And sine 4 pi over 5 equals negative sine 6 pi over 5. And so what ends up happening is this equals cosine 4 pi over 5 minus I sine 4 pi over 5. And so that looks exactly like e to the 4 pi over 5i, except the I component is negative. So it's the complex conjugate of this value. Well, this value, complex conjugate means same value of a complex number, except you make the I imaginary part negative of what it is. So epsilon squared was equal to e5, e to 4 pi over 5i. We just have the complex conjugate of that. So our value here is the complex conjugate of epsilon squared. So we use an asterisk notation to notate the complex conjugate. All right, and so our last one to do that's difficult like this is C5 4 times. And so that's going to get us e to the 8 pi 5 over I. We're going to get cosine 8 pi over 5 plus I sine 4 pi, 8 pi over 5. So 8 pi is there now instead of 6 pi's. And that actually just ends up equaling, so I can write it here, but that ends up equaling cosine, because cosine 8 pi, 2 pi over 5 equals cosine 8 pi over 5. And sine 2 pi over 5 is equal to the negative of sine 8 pi over 5. So this is looking like what you're going to end up getting is cosine 2 pi over 5, but now a negative because it's negative I sine 2 pi over 5. So that's the complex conjugate of epsilon. So that's what's going to go in here. And again, we put the star notation. All right. So moving on from here, we have sigma h. And if you recall, sigma h, x just went to x and y just went to y. Sigma h was in the mirror plane. So x plus iy is just going to go into itself. So that one you're going to get 1. And then for the S5, right? Well, remember an S5, just like we've been doing this trick throughout this derivation, an S5 is equal to a C5 followed by a sigma h. Well, sigma h we just determined doesn't do anything. So this is going to be the same character as C5, which is epsilon. And for S5 3 times, S5 3 times is C5 3 times followed by sigma h. So it's going to be the same character as C5 3 times. So that gets epsilon complex conjugate of epsilon squared. And then S5 7 times, we've gone through this logic a bunch of times, so see the previous videos, is C5 twice, followed by sigma h. Sigma h does nothing, so this is just equal to epsilon squared. And then S5 9 times is the same as C5 4 times, followed by sigma h. Sigma h does nothing, so it's just going to be the same as sigma 5 4 times, which is epsilon complex conjugate. This is a squared. So at this stage, we just need to figure out what our remaining values are there. And the way to do this is if we call this some value A, we know 1 plus 1 has to equal what we started with, 2, and A plus E is going to have to equal what we started with. So that means that A plus E is going to have to equal to 2 cosine 2 pi over 5. So we're going to do this in another video just so we have more room and I can erase this.